much. So I will present some results of the work which is still in progress, and I'm doing it with Kasia Karnas. And yes, there is still much to do, but we already did something, so I can speak about it. So first of all, maybe I will define what does it mean that gates are universal. So I start with some group G, which is compact and connected. This is a Lie group. And then I consider a set which is generated by some elements. So I choose the elements G1 to Gk from my group, and then consider any possible word in these elements. And if all these words are dense in the group, then I say that elements G1, Gk generate group G. Then I have to switch to another language, and I will call element of the group a gate. So G1 is a gate, Gk is a gate, all those elements are gates. And then I say that gates G1, Gk are universal if they generate a group. And I already said what does it mean to generate a group.
I'm going to discuss unitary matrices, unitary gates, or not?
Yeah. Mostly unitary. But like definitions are universal. So this is example. So first example is I start with one gate which belongs to the group SO2. And then I ask when this gate is universal, so generate the entire group. So what I can do is just take this gate and multiply it with this gate and do it many times. So it will generate my group if this angle phi is a rational multiple of pi. Yes? If I have a rotation, which is
these are three-dimensional rotations.
it's SO2. It's on one plane.
So it's now.
It's very simple example. I just wanted.
Okay.
Yeah.
What is KZ?
So Kz means that this rotation is about axis z. So my axis will be always
The
one.
group doesn't know about
Yes, but this is just by introducing some notation. When I have a rotation, I will rotations will be called by O, phi, and k is the axis of the rotation, and phi is the angle of the rotation. So just to specify notation, I wrote it here. Good. So we know when SO2 gate is universal, but now assume that you have SO2 gate which is not universal. And maybe if you use more modes, so you allow this gate to act on the three-dimensional space. So you have x, y, z, and then you can rotate around z-axis, x-axis, once again z-axis, y-axis. So you consider this kind of matrices. So perhaps even though for rational theta this does not generate SO2, but maybe it happens that when you put this SO2 group into SO3 in three different ways and consider this kind of generation, you will get entire SO3. And if you get entire SO3, then of course you can get SO2, because SO2 is contained in SO3. Is it visible? Like hardly. No, it's just because I cannot make darkness in this film. So.
But you cannot guarantee that you will be back exactly in the original SO2. You can approximate the original.
Yes, of course. That's true. It will be. It will contain my.
The group, you can't really get back.
Yes. So.
This is physics for all practical purposes.
No. It will be after closure. Yes, if I take a closure of this cell, because saying that it will generate SO2 means that it will be
So
dense.
you take this element and you add to this two additional rotations.
Yes, but exactly by the same angle.
But
So
you can think it is that you have a box, a black finite box which rotates around some axis. It depends
Yes.
how do you connect it.
And then you
But this is a single rotation, but you can connect it to this, to this, axis, or to this axis, or to this axis.
Okay, so another problem. So of course you cannot generate SU2 using only one gate, because SU2 is non-abelian group. So you have to start with two unitary matrices. Once again, this is only some notation, these angles and axes, so you should not pay attention to it now. So you need two gates to generate SU2. However, you can actually use one gate if you take it, and then you take the same gate with modes permuted. So like the first mode becomes the second, and the second becomes the first. So then these matrices might not commute, and if they not commute, then they can generate something non-abelian. And in some cases it might be entire SU2 group. But if this does not happen, so you don't get generation of SU2 by your two elements, you can do the same trick. So take those two elements and allow them to act on three modes. And then probably, or they might generate SU3. And then you can go back and get SU2 after closure. Okay, and you can consider general situation. So we take a gate from SUK, and then you consider the set of gates which is generated by these gates when you apply permutation of modes. So you conjugate this gate with all possible permutations, and then you ask whether this thing here generates you. And so the first question is, when is this set UK universal on SUK? And if it is not universal, is it true that if I put it into some higher dimensional group, SUK plus n, then it will be universal? And what is the n which is needed? So we do not know answer to this question yet. This is like the problem we still work on, but we have some progress. Okay, so now I will speak about how to attack these kind of problems. And one of the crucial things here is Zariski topology, and that's why I have to actually define it, because probably it's not so well known. So typically topology is defined by saying what are the open sets. So I say that in my space open sets are like this, and then the topology is defined. But in Zariski topology you do it other way around. You say what are the closed sets. So a set is closed if it is a zero level of some finite number of polynomial equations. So we have a space, for example, Cn or Rn, and on this space we have polynomials, and then we take some polynomials and look at the zero level of the equations given by those polynomials.
What is the zero level?
If you have
Polynomial equal to zero.
polynomial equal to zero. Solutions, yes, solutions of the polynomial equations. Good. And then those sets which are given by the solutions of the polynomial equations are closed, are Zariski closed. And Zariski topology is a topology in which closed sets are Zariski closed. So what is a very simple example? So if you take complex numbers, then the closed sets are only finite number of points. So this is a drastic change compared to the standard topology. Because when you take polynomial in C, you can have only finite number of the solutions for this polynomial equation.
So why internal segment of a line is not a closed set?
So you have to find a polynomial which is defined in C1, which will have it as a solution. This is impossible. When you have a polynomial in one variable, you can have only finite number of solutions. Good. So this is Zariski topology. So set is Zariski open. It's actually actually a very strong statement that the set is open in this topology because it's both open and dense in the standard topology. So after closure, if you have an open space in the Sawicki topology and you close it, you get an entire space. Yes, and so also boundaries of open sets have nice structure because they are given by those polynomial equations.
Should we really believe that changing the topology in such a simple case as SO2 groups can lead to some result?
It's not that I'm not changing it to have
You're using a different topology.
Yes, and I'm using it just to compare abelian and non-abelian groups, which I'm now going to do. So wait a second and you will know why I'm saying this. I'm introducing this topology. Because
May I tell something? Okay, this is a language you can describe this, and you can use example where on the previous transparency there are strong connections between the normal topology and the Sawicki topology, and this is how you do it. Okay, so topology of the group is always the same here, which is used, but you describe this in terms of the Sawicki topology, and then make the connections to the real topology. Okay, normal topology.
okay, good.
So we still can think of normal view of continuity of the group.
Yeah.
Yeah,
Nothing
sure.
changed. Yeah, you can still have like the normal picture in mind, right? This topology is just nice to describe something. That's why I defined it. And besides, it's you have to learn something every seminar. So this is like one message you can take home, for example. Good. So we have a group. So now I will compare generation of abelian and non-abelian groups. So if I have a compact abelian group, then it's torus, n-dimensional torus. There are no other groups which are compact, connected, and abelian. So, for example, SO2 is a torus. It's actually circle. It's one-dimensional torus, and we know that it's generated by any element if the rotation angle of this element is non-rational multiple of pi. So actually, it's the same kind of fact is true for any torus. So when I have a torus, then it's generated, then its generators, so elements which generate my torus, they form an open, actually not open, they form a dense subset of the space, of the entire torus, but it's not open and there are no interior points in the set of generators. So if I take a generator and I consider a small neighborhood of this generator, there is always an element which is not a generator. So this set is not open, so it's only dense. And it's very different in case when you consider non-abelian groups, and these are quite old theorems, and not many people know about them because I was giving similar talks in a few places, and
Sorry, I knew.
yeah, I know that.
You are very familiar.
Exactly. Good. So if the group is non-abelian, then you have to consider a set of pairs. So we take G times G cross G. And then pairs which generate a group, they form Sawicki open set in G times G. So you only need to know some polynomial equation to, so elements pairs which do not generate your group are solutions of some polynomial equations defined on G times G. So it's it's much more likely, I would say, that some pair generates a non-abelian group than something generates a torus.
But these polynomials are in what variables?
In variables defined on G times G.
Coordinates of the
So-
group.
Yes, so you coordinatize G,
Yes.
and then these are polynomials.
Yes.
Even though it looks rather peculiar that you have angles, for example, and take polynomials in angles.
So angles are just for spectra. There are some other parameters in this. assume that they are chosen in a good way, and so.
You really need some assumptions on this, because if you take G to be a direct product of something A, B,
Yeah, so let's say that when I take G now, so when I was speaking about this arraysty and so on, so I treat G as an algebraic group. So G is it has a structure given by polynomials, and so it has. Then it's okay. So I treat G as an algebraic group, and then it's well defined. Okay, so another thing which will be useful is something called finite covering homomorphism. So if I have a compact connected and semi-simple group, so there are not all assumptions are needed, but I wrote them. So I have this kind of group, and then I have a map from my group to some other group, and this map is a finite covering homomorphism. So it's a homomorphism, and covering means that it's onto H, and finite means that over any element in H, there are finitely many elements in G. So then if G1, Gn generates G, actually it's if and only if, so G1, Gn generates G if and only if its image under this finite covering homomorphism generates H. And what I will aim to do is to show that a joint representation is kind of homomorphism. So a joint representation is defined as a map from G to automorphisms of the Lie algebra of G. So it's just conjugation by elements from the group, which acts on the elements of the Lie algebra. We all know what is a joint representation, I think. So then I take, so in order to prove that this is a finite covering, I have to look at the center of this map. Because when G belongs to the center, then add G is equal to identity. Yes? So what do I know? I know that the image of add G, acting on G, is G divided by Z of G, which is a projective group of G. And so now if I assume that this center is finite, then I know that a joint representation is a finite covering homomorphism. And I also know that if G is compact, then it possesses some invariant G invariant inner product, which means that actually matrices from add G are simply orthogonal matrices acting on my Lie algebra. So on some space, I can take some linear space which represents my Lie algebra and define orthogonal group on it. Good. So how can we use it? So now I will assume that the center is finite, and I will make one more assumption, namely that this projective group is simple. It could be semi-simple, so then it will consist of several simple components, but just for simplicity, assume now that it's simple. For example, if I take SUN, then PSUN is simple. So it has no normal subgroups of any kind. Then Lie algebras of the projective group and group itself, they are the same, and they are simple Lie algebras, which means that there are no proper invariant subspaces with respect to the action, with respect to the adjoint action. And now this is like the crucial point now. So I denote by LG of my Lie algebra all endomorphisms which commute with add G, which commute with the adjoint action for all elements G, so for entire group. And then by SGH, I denote the solution of these two equations. So something which commutes with add G and add H only. I do not assume that it has to commute with anything else. And then I have a very nice nice theorem which says that if I only assume that GH, so the group generated by GH, is infinite, then this group generates entire group G if and only if this solution set is the same as this space. So in one direction this is a trivial statement, because if this is an infinite group and if it generates G, it must be like this. Because any element R for any G is constructed from these two operators. So then if something commutes with all, it also commutes with this. But in other direction, it's not so trivial, and I will not show you a proof. However, it's really simple, but we perhaps won't have time for this, because I want to show you more examples, not like some general statements. Good. So how about, so this proof is basically based on looking at other G invariant subspaces, and also using this finite covering homomorphism property. But it's really, really simple. And now, how about when this group, this projective group is not simple but semi-simple, it consists of a few components. Then what I have to assume is that GH is infinite, but also its projection on every component is also infinite. This would be the case, for example, for SO4, because SO4, if I take a projective group SO4, then it's the product of SO3 and SO3. So it contains two simple components. So then I have to have that the projection on every simple component also is infinite. Okay, so let's look at SUK, because this is like the most interesting group for us. Of course, it has a finite center, because elements which belong to center are alpha identity, where alpha is root of a unity. That's why a joint action is a finite covering homomorphism. And we also know that the projective SUN group is a subgroup of SON square minus 1, because so a joint action takes my group into a group which is orthogonal group of the Lie algebra, and the Lie algebra has dimension Sn and n square minus 1. Which means that PSUN is a simple group, and actually I should say we also know that PSUN is simple group, because it does not follow from this step. But what we know about a joint representation of SUK is that it's irreducible. So immediately I know this space, LGG. These are all elements of the type alpha identity, where alpha is any complex number. So two matrices, U1 and U2, generate my group SUK, if and only if they generate something which is infinite, and matrices which commute with add U1 and add U2 are only alpha identity. So I have a very nice condition. So what is left now, and is actually the most difficult part, is a characterization of pairs which generate infinite subgroups. And to do it, I will use some tricky inequalities. So I will assume G is either SUK or SOK. I have for any two matrices, A and B, complex or real, I can define inner product just by trace AB star and norm of the matrix, which is square root of A star. This is a standard thing.
Star is Hermitian combination.
Yes. But when I speak about SOK, then star will be just transposition, because everything is real.
So in physics we would call it the diagram.
Dagger, yeah. This is dagger. And now what I will need is a group commutator. So I will denote it as a usual commutator, but with a dot here. And commutator of A and B is AB, A2 minus 1, B2 minus 1. So if matrix is a commute in the usual sense, then this group commutator is identity. Yes? So it's just measuring non-commutativity of elements in a group, but using a allowed operation in a group, which is multiplication, not addition. Good. So now when I have matrix A and B, which belongs to SUK or SOK, then I can consider a group commutator, and I have following inequalities. So the distance of the group commutator from 1, which measures how much they do not commute, is less or equal square root of 2 distance of A from 1 and distance of B from 1. This is a no. Good, and the other statement is if AC, if the commutator of AC is identity and B is and the distance of B from identity is less than 2, then A and B also must commute. Great. So these are some inequalities, and now we have to make use of them. So what the other thing which I introduce is B with this index 1 over square root of 2. And this is a ball which is centered at I, at identity. And so these are all elements which are for which distance from the identity is smaller than 1 over square root of 2.
This is not the power.
It's not a power. This is some index. It's maybe a quite unfortunate one.
Because one can also define the power.
We will take powers soon. So now the theorem says that if GH belongs to this ball, so if the distance from the identity is smaller than 1 over square root of 2, and if those elements do not commute, then they generate an infinite group. It is, and you can deduce it just using those inequalities, and you do it by showing that the sequence, so the sequence you should consider is G0 is equal to G, G1 is commutators of G0 with H, Gn is commutator of Gn minus 1 with H. And then when you look at this inequalities, and this square root of 2 is just because of square root of 2 here. So it's designed in such a way that this sequence will converge to the to identity, and it will also never, and this second inequality says that it will never, there won't be any cut, so there won't be any n for which it will be identity. So it's like really converging to identity, and it means that it is infinite.
And the square root of 2 is essential if you take a different...
Yes, if you take a bigger ball, then it won't work so
No,
nice.
smaller.
So, for smaller it's okay. It's
Ah.
okay. You want to have as big as possible, because then
The largest. One single question concerning notation. This is not a bracket of the second. GH is here now. It's a group generated by 2 elements.
Yes.
The group,
These brackets are group generated by 2 elements. Okay. Okay, so now we can actually compute it. It's not really difficult, because what I have to do is compute the distance of G from I, from identity. So it's trace G minus I, G star minus I, so it's trace 2 times. Yeah, these are formulas here. And so these formulas depend only on spectra, because it's given by traces of matrix G and G star, and trace depends on spectrum only. So if I take a matrix from SUK, I have spectrum like this. For SO2K, so I have to pair those elements. So if I have E to I phi 1, then I need to have E to minus I phi 1. Actually, probably I should not write it like this, because it's slightly weird to speak about the spectrum of the real rotation using complex numbers. But anyway, I can always diagonalize any matrix. Sometimes it's not very meaningful, but let's do it. and the same for SO2K, this condition translates to some simple inequalities. So for SUK, you have to take sum from 1 to k, sine square phi I divided by 2. So you take spectral angles, divide them by 2, and take sine square of them, and this must be less than 1 divided by 8. This is equivalent to the condition here. And also similar inequalities you get for orthogonal groups. Good. So this is one step. So we know that G belongs to this this ball which is centered around identity and has values 1 over square root of 2, if and only if angles phi I belong to some small neighborhood of 0. Yeah, because look, these things here, they are all positive. So those angles must be very small. Maybe not very small, it depends on how big is K.
Groups must be very
Yeah, very small. So then you will say, oh, so this is not really good, because then you know about generation of infinite groups only for a very small rigid volume group, yes? But if G does not belong to this this ball, you can put it inside just by taking powers. Yes? So for every element of your group, there is a power such that even if G does not belong to this ball, then G to the n belongs to this ball. And this is an operation we are allowed, because this is like just taking this gate and multiplying it with itself n times. So I know that I can move element G to my ball, but then I want to know if there is some global n, such that if I take this, yes, so I need some constant ng, such that for every element G, Gn will belong to my ball if n is between 1 and ng. So there is, so if there is some, I want to have a global n for this moving into the ball.
Universal for all groups.
Yes, exactly. Universal for all elements. And there is a theorem which says it's true if your group is compact. And it's I will show you a proof, because it's easy. So the proof is like a usual proof when something is compact. So for every G, you know that there exists such an element, such a power which moves it to my ball. Good. But if ng moves G here, then it also moves some small neighborhood. And I can do this kind of neighborhood thing for every element. But now I have to use the fact that the group is compact. So those open sets which I just defined, they form a covering of my group. But if the group is fine, if it is compact, then any covering has a finite covering. So I can obtain from here, from this infinite covering, finite one, and then I can define ng as a maximum over this finite set. This is well defined.
Is it important that the radius of this ball is 1 over square root of 2?
Yes,
It is.
very important.
Not in this proof, but
Not in this proof, but
This proof not.
in the proof not, but at the very beginning it was important, because in the inequality here you have square root of 2. Okay, good. So we know that we can move elements into the ball. However, sometimes something wrong can happen, or bad, let's say, that when I start moving my element, it is moved into identity. And if it is moved into identity, it's bad, because then it will commute with everything. And then I cannot use the argument for generation of infinite subgroup or infinite non-abelian subgroup. So there are two types of elements. Let's say element G is a good element, so I take it, then I take its second power, third power, and I'm in the ball, and it's not identity, so it's okay. But then there might be some elements of the type that I take h squared, and then h to the power 3 is already identity. So it's that. So I have to specify, I have to specify when this kind of bad situation can happen. And this is just some playing. You have to play with those angles which define the spectrum of the matrix. So spectrum is defined by some set of angles.